Okay. Welcome back to the third and final talk of this morning's session. For this talk, we will have Pranendu Darbar from Max Planck Institute in Bonn, who will tell us about the extreme values of Dirichlet functions.
Yeah, so I'm grateful to part of this nice conference, and thanks to the organizers for your effort to make this such kind of beautiful conference on especially on circle method and subconvexity bound of defined L functions. So I am not working on those delta method, etc., but I will talk something about the extreme values of Dirichlet function, that is kind of like different direction. Instead of looking at the upper bound of the L function, just look at the lower bound and what it says about its extreme values. So my goal is to understand various kind of Dirichlet function. Those are just GL1, and look at those kind of L function inside the critical step, and what is the growth of those L function inside the critical step. So this is your half, this is one, and especially I am looking for various kind of GL1 L function. So I'll define few of them. So you can start with your famous zeta function at half, where I am looking at the zeta function on the critical line, and I am choosing the t which ranges from t power beta to capital T, where your beta is some fixed number from 0 to 1. Also, you can speak something about any dyadic interval as well. So this is the first family, and second one is the L function, Dirichlet function at half, which connected to the quadratic Dirichlet character. So D is your fundamental discriminants and D is of size x. So this sign means if D is of size x, that means D lies in between this dyadic interval. This is the second family, and we know this is kind of unitary family from the random matrix theory, and this is connected to the symplectic family. And their analysis is a little bit different in terms of how the corresponding characters behaves. And third, I also looking for the L function for a fixed Dirichlet character of some modulus q, and you are varying in the t aspect. So this is the three family I am looking for. Also, you can consider the other famous family, that is the character central at the central point, values at the central point of certain modulus q. So this is the famous four family of NG aspect. So let me start with what we know something about the omega result of the unitary family zeta, and we'll see also the upper bound as well. So let me start with the zeta function. So zeta half plus IT. So this is some under GRH. Let me formulate about the history of the upper bound and the lower bound of the zeta, and this is unconditional. So we know that under Lindelof hypothesis, this is bounded by t power epsilon for any epsilon positive and t tends to infinity by Lindelof. And I just skip all those very tiny details like t should be bigger than equal to 2, etc., and modulus also. And if you know GRH, then you can do a little bit better. So it is exp of some constant time double log t divided by log t. So I will sometimes write log 2t is uh, log t. So this is, we know, this is under GRH. And we know, based on unconditional Weiburga, that your zeta of half plus it is bounded by t power 1 by 6 minus 1 over 84 plus epsilon. And this is kind of subwell bound. As we saw from last talk, they are trying to find about the subwell bound for the GL12 function. So this is all about the upper bound, and we know, we saw a lot of lectures about how they use this subconvexity technique to find some upper bound of the various kind of higher degree L function. So then, what about the other way around? I mean, what can we say something about the omega result? C is some constant, poetic constant. Yeah, any fixed constant. Well, so I think yeah. Yeah, so if I move towards the omega result, then it is known by Montgomery that if you look at the maximum value where t varies to 0 to t, zeta of half plus it is equal to omega of exp some constant time square root of log t divided by square root of double log t. And I think C is here 1 over 20 in his paper, but it is again, this is under GRH. So, so then Bala Subramanian, I can say Balu and Ramachandra able to remove this GRH condition, and they have, I think, couple of papers to find out what is the improvement of this constant, and they have constant for C equal to 0.0530 dot, and this is the constant they got by using the movement method. So you are basically computing higher movement of your zeta function by looking at they found using movement method, and then Sundarajan comes up with some new idea, so-called resonance method. So this is called resonance method, and he also able to get the same kind of bound. I mean, in terms of the order of magnitude, is here square root of log t divided by square root of double log t, but he has constant c equal to 1. So that means there are two parts to look at this kind of problem, and order of magnitude is so difficult to get in terms of this omega result. Also, there is another aspect that is whether you can improve this constancy. And then this result, I think, comes in 2006, and many people was working on this kind of problem, and until there is a breakthrough work of Bondarenko and Safe. I think around 2015 or 16. And they got some breakthrough result by improving this result of Sundarajan by getting this uh, extra triple log of t factor inside the square root. So they got zeta of half plus it is equal to omega of c exp of c times square root of log t triple log of t divided by double log t. So this is very nice piece of work by them. They able to uh, give a new idea by modifying the sounds resonator method, and this resonator method is called something called long resonator technique. I will explain all of these. And first I will explain about the resonance method of sound, then I will go into how they got this kind of improvement with extra triple log t factor inside the square root. And they basically have this Bondara concept, they basically have couple of papers again by improving this constant. So one paper, the first paper was like this constant was 1 over square root of 2 here. And then they improved this constant later on with c equal to 1. So here basically in this paper they looked at I mean whenever you are looking at this kind of method you have to find out some kind of approximation of your zeta at half, right? So they use just yeah that also will depends on beta. No, it will not work in the dyadic interval. You need some. Yeah. Yeah, they have some condition on the beta and etc. So I just want to forget about that constant. Which one? No, that will not work.
No, this is much longer than the dyadic.
This is much longer interval, yeah. So because whenever you resonate, you use the long resonator inside that segment t to the power beta to minus t to the power beta to beta, it would be the error term will be very large in that case. Yeah. And they got this constant, this c. I mean they have this improved constant c equal to 1. Then so first let me say something about what the technique they use. So first they use obviously long resonators. Second they use positivity of coefficient of resonators. And third one they use sub GCD sum. So this GCD sum, just I will explain in one word that this sub GCD sum will look like you are counting some integers in a very sparse set, Mn, and then you are doing GCD of Mn whole power alpha divided by LCM of Mn whole power alpha, and then you are taking supremum of this M, which is of cardinality n. So you have to find some nice nice upper bound or some kind of exact value of this kind of GCD sum. This is called Gall sum, where alpha is lies between half to 1. So in the problem of zeta function, your alpha is half. So you have to find some nice formula for this one. And they able to connect this Bondurant concept. They able to connect this problem to the sub GCD sum. So this is just a full GCD sum. And sub GCD sum is that you are just considering subset of integers where this M divides M. So this becomes a subdigital sum in that case. So this is the technique they use in their paper, and later on, the current record is C equal to square root of 2. This is by varieties. Yeah, so whenever your beta is close to what? Yeah, depends on beta. I mean, see, in optimized sense, you will get this constant as square root of 2. Yeah, when you can take beta is close to 0, then you will get. I don't want to make that statement very big, you know. Yeah, but you can choose your beta. You have that choice of beta in your hand. Okay, I will say something about this. This C beta will depend on some beta which is belongs to 0 to. Okay, let's say. Okay, this varieties and Tenbaum. So they have this kind of improved constant, and they basically solve this full GCD sum. So, I'll start with this technique of sound. So basically, the goal is to understand the integral minus infinity to infinity RT square phi of smooth function t to 2t, or in the for sounds method he considers this dyadic interval, and you also consider this m2 which is minus infinity to infinity, your zeta half plus it RT square, and where your RT is called resonator, m is less equal to some height n, m power minus it. This is called resonator, which basically this basically resonates with this zeta and picks up its large values. So this is if you just forget about RT square, it will give you some t times log t square. So this is very small if you like to find this kind of omega real. So you need to apply some kind of dummy object here at which this zeta, if you integrate zeta against the resonator, then it can pick the large values from there. So here the OA sound choose this resonator. So he choose in the square phi OA. I mean, if you look at our prime, this resonator will look like this is square root of log n double log n divided by p power half times log p, if your p lies in this interval log n log 2n less than p less than some big power of log n, and it is 0 otherwise. And as he was working on the square phi integers, the other values is 0 if your k is greater or equal to 2. So this is sounds method. So as you see, he is picking up all of the integers which has some certain height up to n. And now if you if you want to compute, I just want to compute some few steps of this integral m1 and m2, at which you can understand where this kind of result of the Bundarenko shape, they got this improvement. And so let's just try to evaluate these integrals m1 first. So m1, if you expand your RT square, then we'll end up with mn, which is bounded by n, and Rn bar. For now, we just take this maybe a complex number, this Rm, and the integral minus infinity to infinity m by n whole power it and phi of. So now basically this kind of integral depends on how this frequency oscillate, right? So if your n is equal to m, this will give you the main term. Otherwise, they have a lot of cancellation in this integral. So if you use the Fourier inversion, you will end up with mn, which is bounded by n, then Rn bar, and phi hat of t log m by n. And you have, you know the sum. So this is phi hat of y with the inverse Fourier transform, phi t to the power minus ity dy, and you know some good growth of this function. So then everything matters when we need to consider this n is bounded by t power 1 over epsilon. So you have to focus on this interval to compute this kind of, to take control of these frequencies. So once your n is less t power 1 minus epsilon, then if your m is not equal to n, then this t log m over n is bigger t power epsilon, so that your quantity t log m over n is bounded by t power minus 2, depends on the epsilon you are taking, depending on the growth here. So in that situation, when your m equal to n, then you will get the main term. So in that case, you will have t times phi hat of 0 and Rn square, n is bounded by n, plus big of t inverse n less equal to n Rn square. So that means if you take this whole thing outside, then you will end up with 1 plus big O of t inverse, and this is very small, and you will have your second moment of your coefficient of your resonators. So this is by Cauchy-Schwarz. So you will have your main term t times some factor which depends on your smooth function, and this is very little term here, and you have the second moment of your resonator, coefficient of your resonator. And then if you similar way, if you compute m2 in similar fashion, so here you have to use the approximation of your zeta. So you can consider zeta half plus it equal n less equal to t in power minus half minus it plus big O of t power minus half. These approximations are true only when t is of the size capital T. So we are looking at this one as a dyadic interval. So once you plug in this approximation inside this integral, then we'll end up with something like t times we had 0 mk equal to n, which is bounded by capital N Rn bar divided by k power half So if you just truncate and take K here, just to realize that this is exactly similar. And then you have plus P go up T power half times so then from here you can notice that from these two quantity you can say maximum of this T lies in diary interval is bigger equal to this ratio M2 divided by M1. So basically you have to find the ratio M2 by M1. So that means your maximum of T is of the size T half plus IT would be bigger than 1 plus P go of T power minus 1, and the ratio is here Mk equal to N, which is bounded by N. This is very much important. Rn bar divided by K power half, and you are taking the another ratio which comes from M1 sum, which is nothing but N bounded by N. Rn square. And obviously you have some kind of modulus here. So basically now you have to struggle with this kind of optimization problem when you are varying your resonator. I mean, in which way you will choose your resonator, and the sound found that this is the kind of optimal resonator you can choose in this way. So then if you look at this quantity here, then he able to prove that if you take maximum over all R is the resonator, then I'll name it just as capital R maybe. Again, this is equal to exp of square root of log n divided by double log of n and times 1 plus some little of 1. So this is the exactly equal. So able to solve this optimization problem in this the way he took the resonator. So if you plug in this one, this multivariate function, then you will end up with this problem. So that means the problem here is that you have some kind of partial sum, right, in this whole ratio. So you have to first consider the whole series, right, to look at what is the main term there, right. So basically you will get some kind of Euler product, right. If you take it as a full series, then you have some tail part. So that is kind of tail part of the series. So this is kind of error term here. This is going to be error in this choice. And as you are taking the whole series, you will lose many things here. So you have to be very careful whenever you are choosing something there's something like about the coefficient of the resonator. So that is very much important. I mean, so once you are computing some kind of Euler product, so basically you are integrating something, and in that integral, the main mass will be around this interval of prime. So mass will be basically located in this interval. So you can't find any other choice of your resonator at which you can get the optimal value. And this is so balanced because this kind of range will come by comparing whenever you are compare the Euler product and its tail part. So this is very much kind of optimized. Well, so now we have a little bit understand about how the method of sound works here. And then we'll see the new idea of Bondaran concept in this family. So is there any question so far? dedicate L function? Yeah, you can do that. Yeah. Yeah, that point I will come because yeah, I mean the sounds technique you can apply for dedicate. This is very versatile. I mean you can apply from cast form. I mean other degree L function as well. Because I mean they just look at the resonator in this way, so they don't have any complication in this problem. But I will explain while I will look at the improvement of Bundarankan shape, why that method is not that versatile in that sense. Well, so now if we look at the method of Bundarankan shape. So while their idea comes like this, so in sound he's picking every integer until some certain height n, right? So that's why you don't have kind of allowance to go beyond t power 1 minus epsilon, right? So you are somehow bounded in some sense. So what Bondareng and Safe's idea was, don't just look at the integers up to certain height n. You can pick very large integers, but you have to choose some kind of sparse subset of the integers. So your integer can be very large, let's say n power log 2n. So you can pick those integers, but you can't pick every integers inside this line. So you have to be very careful. You have to choose in some dyadic intervals. And let's say I will name it as pk, the primes, because we are always looking at primes whenever you are looking at whenever you are talking at some resonator, right? You have to just looking at the primes, then you can extend to the any multiplicative function. So look at this interval pk. So you are first picking this interval. So that means if you take some prime, that will be bounded by some e power log n, double log of n, which is bounded by p, and here it is e power k plus 1 log n log 2n. So this is very small interval, right? It's a dyadic interval, and you are taking k is 1, 2 up to log 2n whole power gamma, where gamma is less than 1. So you are basically focused on this kind of very sparse subset of your natural number, and also you have restriction that you can choose how many prime factor inside this interval. So that means, so you can choose, so we can choose, at most a log n divided by k squared times log 3n many prime factors from this interval, which I name it as pk. So you have to then make a sequence up to k equal to 1 to log 2n whole power gamma. So you have to take very sparse subset of this natural number. So you are not picking this kind of dyadic interval. You have to choose some subset of primes which you can choose at most a times log n divided by k squared times log 2n, and you have such kind of relation for your optimization. You are picking a times gamma is bounded by 1. And the main next problem is that whenever you are taking some sparse subset, you have to prove that this sparse subset is bounded by some kind of number that we are taking for the sounds resonator technique. That means you have to prove that the cardinality of the set m equal to n, and the m is, I just name it as, you are taking this kind of, this is pk plus 1 and up to p log 2n whole power gamma plus 1. So whenever you are taking this kind of interval, you are taking the union of all those sub intervals, and then you can form this set M via this. So in other word, I will write in a for the sake of completeness log 2n plus gamma and your pk. So you are picking up all those this interval of primes. So next, the difficult part is that you have to show that this cardinality of M is bounded by the capital N. So basically, to prove this cardinality of M is bounded by capital N, they use heavy masonry about how they are looking at the prime in various subintervals. Also, you have the restriction that you can choose at most A log N divided by K square times log 3N many prime factors. So this basically restrict you to achieve this kind of bound. Then you can choose whatever you like in terms of T power 1 minus epsilon or something like that. So you can choose those element. So so now if you look at in this Euler product here, so if you look at this Euler product, now you have to struggle with not this kind of integers. You have to struggle with the integers which lies in this inside this set the script of M, right? So you have to work with some kind of very big Euler product, and you have to take control of your tail part, because that is also very much important. And I would just write down what the resonators they are taking here, at which you can see the differences between the sound and the resonator of Bundren concept. So the resonator they are taking log 2n, log n, log 3n, log 2n divided by log 3n, and 1 over p power half times log p minus log 2n minus log 3n. And if you have this kind of your p is in between e times log n, log 2n, e power log 2n whole power gamma, yeah, and you have this e times log n log 2n, and this is 0 otherwise. They also they also picking like in the same fashion in terms of your square free integers. So here is nothing about to controlling some to controlling the integral in the initial point. So that's why they are taking just e here. So if you integrate the whole Euler product in this situation, then they can gather many large values in terms of they are getting extra triple log factor in this way. So that means whenever you integrate, you will gathering more mass around this interval you are taking of primes. So that's their idea. So first, this is the first kind of idea, but there are many obstacles whenever they are applying to the problem. The second obstacle I would mention that, so I already compute something the integral m2, right? Let's look back to the integral m2 again. So now your resonator would be r of m, sorry, r of t would be rm m power minus it, and you are taking your m from the set the mathematical of m, right? So script m. So now your resonator has been changed, and this coefficient is determined from this setting. So now if you compute your integral m2 in this way, you will, so they are as Arko said, they are looking at some kind of long interval t power beta to t, and so if you evaluate in this way, then you will get some kind of t divided by log t, and then you have this element mn belongs to m, and you have k is bounded by t, you have rn bar divided by k power half, and you have phi of t, So they just take t by log t, but you can just remove log t factor as well. You would still, you can integrate anyway. Km by n. So if you integrate full integral, not the subpart of that. So once you are in this situation, that now again next problem is that whenever all of your integer is bounded by capital N, then you can correlate between these two elements. But now you don't have any correlation because this is kind of very sparse set, and this is at some height t. So they don't have any correlation. So now you got stuck. What to do next part? So next part is that what machinery they are using, you just take the positivity of the coefficient. So if you take, you need the lower bound of this element, right? Because you are trying to estimate some omega result. So you need the lower bound of M2 because you want to find M2 divided by M1. So lower bound is enough. So if you want to find the lower bound, you can throw, so if it's positive, there is no bar here. So you can throw many elements from this set k is less equal to t. So that means you can just work with some element which is of the form m n belongs to m, and I have t divided by log t, and here you have k also belongs to your m, and rn divides by k power half, and you have this factor. Also next step is that also you need some positivity of this guy also, right? So you need some positivity of this guy, and they are taking the Gaussian function. That means you can take phi t is equal to e to the power minus x square by 2. So this is positive, so you can directly apply the positivity of this element. Also you can apply the positivity of the coefficient of the resonator. So you can throw many terms from these summations, and then you can try to how this frequency is fluctuating around the point 1. So then you can say something about when km divided by 1, which is around 1 over t. So whenever you know the information about when this ratio is centered about 1 with some measure 1 over t, then you can manage to handle this kind of frequencies. And you can see that you can also take the subset of this subset of the GCD sum. Now you can connect this sum to the GCD sum I wrote down there maybe, yeah, here in the GCD sum at alpha equal to half with some defined coefficient. You can plug in some coefficient here as well, some f of m, f of n. So still this will not affect anything about the system. This will still remain same. So and you can add another factor that the information whenever you are evaluating this estimate, you can remove this one. You can plug in the condition k m equal to n, because that is the main point. That is the frequencies that give you the large contribution. So once you have this relation, then you can use the relation t divided by log t, and you have mn belongs to m, and you can your integers m basically dividing n, right? So you will have rn, and then divide by n power half here, and rm n power half here. So this is called sub-GCD sum. So that means if you use the condition m divides n at half, then this is bigger than the sub-GCD sum you are taking. Everything is positive, so it makes sense. So now, once you know about what will be the quantity, this quantity is nothing but this exponent here. So if you want to evaluate, then it would be exactly the same. And basically also I would mention where these derivatives and tandem succeed to to got these constants something like c equal to square root of 2 when beta tends to 0. So they basically uses instead of sub GCD sum, they completely solve this problem GCD sum. So if you solve this GCD sum, they basically got this. This is exactly equal to this quantity. Instead of t, you have the capital N because you are measuring the set of all events which has cardinality n. So they completely solve this problem, this Gauss sum problem. And how you will connect those full GCD sum, because you have here one dimensional, right? You have two dimensional here. I mean, two variables are floating around. So how can you connect this full GCD sum? Then you can take the second moment of the zeta function. Then you can have more variables. So you have now 4 variables. So you can easily connect these two quantities. So Tenenbaum and Dirichlet, they work with the second moment, and in the work of Bondarchuk and Singh, they just look at the first moment of the Riemann zeta function. So we don't know about whether we can generalize this kind of method to other class of L function, because here you are using heavily stuffs about the positivity of the coefficient. You know, like whenever in the T aspect, I remove those families. Whenever you are looking at this L function, L of half plus IT of chi in T aspect, so you don't know whether it is positive or not. So this factor will occur in this case, right? So you don't know about positivity of the character. So there is nothing known about this family. So that is the kind of disadvantage of the method of Bondarchuk and Singh. They are struggling with this positivity of these elements. So yeah. So but we are thinking of that that can be handled. So we have some kind of theorem. So in 2022, 2023, we proved that so this is joint work with Bondarenko, Safe, Hagen, and Heath. We proved that either there exists a character chi mod q satisfying L of half plus IT maximum of this quantity. For some positive, we don't know about the positive constant because that is expected to be very small. And either this happens, if it is not the case, then or the zeta perform much larger value with respect to Bondarchuk and Singh. That means you can improve the constant of derivatives in 10. So there are this kind of result is called dichotomy result. That means there are some kind of dichotomies going on. So if you are not able to produce some large values of your L function corresponding to some character chi, if it is not the case, then you can even exhibit some large values of your zeta function. So yeah, so and the main problem is still open. You can't do anything else. So but you know, like if you just focus on the character mod 3, so then you can still use the positivity because you have the primes which is congruent to 1 mod 3 and primes congruent to 2 mod 3. So when it is 1 mod 3, you will have 1, right? You have some positive mass around. So you can still apply the positivity there, but we are thinking that we have to prove that whenever you are taking the very large resonators in this way, the density of these primes in sense of they're reacting with the resonators will be very less. I mean, you are basically more towards the primes, which is congruent to 1 mod 3 rather than 2 mod 3. So that means you can split this summation with respect to character we are working on. So you can split into two terms. The primes congruent to 1 mod 3. There you can still use the positivity, and there is another part prime congruent 2 mod 3. So you don't have any positivity there, but still, if you are able to prove that those guys going to some error term, still it works. But it's very hard to find till now. So yeah, I can say anything in that way. Okay, so this is kind of idea what they are doing, but again, so the next problem is that can we improve this kind of result for the other family? So basically, I was interested in the family ID. So can I have 5-7 minutes more, maybe? Because I started a little late. So.
Yeah, sure. Go ahead.
Okay, so I am basically looking at this kind of family here. So here the problem is that so whenever you are looking at this family, so you have to find out what is the character sum of those coefficient, right? So so if you say that n is not square, this is your quadratic digit character, so it depends whether it is square or not square. So this is bounded by without any assumption, this is bounded by your x power half n power 1 by 4 log 2n, right? Now, first obstacle is that because that's why I wanted to first want to understand what is going on in the method of in the method of Bundarengan shape. So if you look at any element from the resonators set of the resonators, then that imply n is bounded by something like n power log 2n, right? So once you plug in this very large quantity here, this becomes very large. So you don't have anything to do here. So what how can we handle this kind of large quantity whenever you plug in here? So that is the kind of next question. I mean, then somehow you have to work with this kind of character sum. You have to need to know how much this character sum oscillate. So that means even you know the GRH, you have this is x to the power half and maybe half plus epsilon, I can say for, and you have n power epsilon here, even if under GRH. So if you, for any epsilon, right? So for any epsilon greater than 0. So still you are in trouble, because once you are plugging this whole very large number, still you don't know what is the exact value of your epsilon. So then in a joint work with Gopal Maiti, we were looking at this kind of problem in function fields setting, and they have more clear evidence about whenever you are working on the irreducible polynomial, and we can still manage this kind of character sum in the function field setting. But in number field, it is very hard to find. So that's why you have to first trying to give a nice formulas for this kind of character sum. And we have some nice version of the character sum at which we can work with this kind of problem in this setting. So it is look like x power zeta 2, and you have some orthogonality mass, which is p divided by p plus 1, and it is your indicator for function of square. If it is square, this term will occur, otherwise it will be look like big O of x to the power half plus epsilon time your term, which comes from the square part, and you are taking n equal to n0, n square, and you have another term, another function which is depend on the square part here. So you can separate the information about how your n is behaving with respect to whether it is square free or this is square free, and whether it is just a whole square. So you can bypass that information about the epsilon in this way. And I must write down what is f n naught look like. It is exp of log of n naught whole power 1 minus epsilon, and your g of n1 is look like b divides n1 mu square d divided by b power half plus epsilon. So this is the part comes from the square free part. This is from the square part. So you have this kind of two estimate. Now you can exactly measure of the epsilon in this case, right? You have exp of log n naught whole power 1 minus epsilon. So you have large. So you can quantify the quality of epsilon in this case, and we uses some zero free region estimate to evaluate this kind of estimate. So then then this kind of amount will kill the large power of your log, and it will still survive in this process. But again, I must say that we can't follow the method of Tenenbaum and Dirichlet because they are working with the square moment, and if you take the square moment in this case, that becomes very large. So you have to stick with the method of Bondarchuk and Safe. So that's why so this kind of technique I also can see that you can utilize this kind of character sum to the other family, like family of the cubic character or family of any higher order character, even for I think cast form if you vary your weight. So I think this kind of observation will work for many families in this way. And I will say the important because you have to assume the GRE. So this is the main assumption. That is the main thing. And that half plus epsilon is coming because you are shifting your line of integration in the Peron integration to the region half plus epsilon. So that's why this is coming up. But if you go beyond half plus epsilon, then you can quantify this quantity. So this is kind of interconnected. This 1 minus epsilon and half plus epsilon. Yeah, so that's it, I think.
Thank you so much. What are some questions for our speaker?
Excuse me. So unconditionally, the maximum absolute value of Riemann zeta function on the line half Bandaranko and Saip result. Of course, if you assume Riemann hypothesis, it is almost O result if you write exponential log t by double log t.
Yeah.
So what is your expectation, whether this could be the correct this
yeah,
one
that,
or that one?
Yeah, that is a nice question.
What is there? That is why I'm asking.
Yeah, so due to Farmer, Gonek, and Hughes, and they conjecture that maximum of the t of size t, zeta of half plus it would be exp of 1 over square root of 2 plus little of 1 into log t double log of t. So this is the expression.
This is the expression. I see. Okay.
Yeah, this is the expression coming from the random matrix theory. Yeah. Okay. Also, if you look at the I think Selbach central limit theorem, if it's uniform for a little bit larger range uniformly with respect to the measure you are taking, then I think people expecting that would be the real.
Yeah,
order of
I understand, but even if you assume Riemann hypothesis, O result will be exponential log t by double log t.
Yeah.
That's the problem. Yeah. Anyway, thank you.
What are some other questions? I wanted to ask you, just like in these contexts where you lose positivity, like here, could you just extremely briefly indicate, like, how does the choice of the resonator react to that? So does R of P remain non-negative, or does it somehow see your character?
No, R of P would be remains the same. Yeah.
It remains the same.
Yeah, it remains the same. It will not interact with the character values. Yeah. Yeah. So that's why I think you have to somehow choose the value of your resonator, because whenever you changing your character value, it will change your sign, right? So you have to very much careful about picking up your resonator. So, yeah.
Thanks. Any more questions? Okay, if not, let's thank our speaker again. That's all for